So if you remember, when we talked about extrema, we ran into a little problem. We were squared away on finding the absolute ones. You looked at the critical points, you looked at the two endpoints, and you just found the functional values. Right? The biggest and smallest ones were it. Finding the local extrema was a little trickier. Fermat's theorem tells us where to look. It tells us if it has one, it's going to be at these points. The points where the derivative is undefined or equal to 0. The problem is, yeah, it might not be. Right? Those points might not be the local extrema. And back when we talked about the absolute ones, we didn't have a way to fix that. Well, now we do. Right? This first derivative test is going to solve that problem. And it's got this very common setup that hopefully you're kind of starting to get used to seeing. Suppose that we have a function that is continuous and differentiable, and C is a critical point. Right? It's a point where the derivative is 0 or undefined. Right? Then this is our rule. This is our first derivative test for determining if C actually is a local maximum or minimum. What we're going to do is we're going to look at the sign on either side. Right? So if the derivative changes from negative to positive, then f has a local minimum. Now think about that. Right? So I have this point x equals c, and I know that on the left side it's negative. That means the function is decreasing. And on the right side, it's positive. That means the function is increasing. Well, think about what must be happening at C. It's going to decrease to here, and then turn around and increase over here. C must be a minimum value. In fact, as we start using this, that's literally what I'm going to do. I'm going to draw a number line, just like we were doing before, and I'm going to draw little down arrows and up arrows to tell me what's going on, and I'll use that to figure out whether it's a maximum or a minimum. Okay, second rule is just the other way around. If the derivative changes from positive to negative, well, if the derivative is positive, the function is increasing. Then when it switches to negative, it's decreasing. That means this must be a maximum. Now, on the other hand, right, there is a third possibility. If the derivative doesn't change sign, it's positive on both sides or negative on both sides, then it has no local extremum there, right? That situation looks either like this or like this, right? And C is this point here at the middle. C actually does have a name. We're going to talk about a little more about that case later on when we start talking about what the second derivative tells us about a function. All right, so how can we use this? So let's take an example, and we'll start off with something kind of simple. It's a parabola, right? So we kind of know how this is going to behave already, right? So let's work through our process here, our new first derivative test, and see how this gives us the answer. So the first thing I'm going to do is I'm going to look at the first derivative. F prime of x is 2x plus 2, and I want to know when does that equal 0? All right, well, that's 2x equals minus 2, x is minus 1. Let me do my number line. I'm going to start at negative 1. Let's see, I'm going to test 0 and negative 2. All right, f prime of negative 2 is, don't lose track of f prime here, it's that function right there, is 2 times negative 2 plus 2, which is minus 2. That's less than 0. The function is decreasing on that side. F prime of 0, on the other hand, is 2 times 0 plus 2, which is 2. That's greater than 0, so it's increasing on this side. Excellent. That's what we expect a parabola to do, right? This negative 1, that's going to be the vertex. All right, so what's happening? It's decreasing and then increasing. This point must be a minimum, right? So this function has a local minimum at 0, comma, and if you go back to the original function, f of 0 is negative 3. That's where my minimum is. And there isn't a maximum, which is also what we expect, right? You know from looking at this leading coefficient here, right? It's positive. This is a parabola that opens up. And we expect a parabola that opens up to have a minimum and no maximum. So it's great. We got what we expected. Our method is working, and we're using it right. So let me give you one. Take a look at this. See if you can't work through this one. Then start it up, and we'll go through it together. All right, so first I need the derivative. And this is going to be a product rule situation. F prime of x is x times the derivative of e to the x plus e to the x times the derivative of x. That's x e to the x plus, let's see, the derivative of x is 1, so that's just e to the x. When does that equal 0? Well, let's factor in e to the x out. E to the x times x plus 1 equals 0. And then we'll set the factors equal to 0. E to the x and x plus 1. The second one, that gives me x equals minus 1. I get nothing from this one. E to the x is never equal to 0. And that's okay. I get only one critical point. That'll work just fine. All right, so now let's see. Let me draw my number line. And I'm going to do -1. Let's test 0 and -2. I'm going to put these into the derivative, right? We always have to keep track of that. So let's see. F prime of -2 is -2 e to the -2nd plus e to the -2nd. Well, look, let me factor this. This is e to the -2nd times -2 plus 1, which is -e to the -2nd. All right, e to the -2nd is a positive number. You multiply it by that negative out in front, you get a negative number. The function is decreasing on this side. All right, how about the other side? What is f prime of 0? Well, this is 0 times e to the 0 plus e to the 0, which is 1, which is greater than 0. So on this side, it's increasing. So the function comes down to this point, turns around, and comes back up. This is a minimum. So the function has a minimum at -1, comma, what is f of -1? That's negative e to the -1st. And that's it. There's my answer. Okay, so those are two kind of basic examples, all right, and some discussion of the rule. We're going to do some more. In the next slide, we're going to go over some more examples of this that get maybe a little more interesting, look at some of the more interesting properties and things that can happen.